Well, good morning, ladies and gentlemen. How are we? I can see the turn-up is not that interesting. Where are the rest? You were a criminal. I've seen you being taken by the TOD. Have you managed to escape? Where is Chok? Please run to the responsible office. Now, as I told you last time, we were able to finish our second chapter, which was the mechanical properties of matter. Are we together? Yes. I humbly and kindly request you to keep silence. Otherwise, you've already offended the academics office. So me beating you or punishing you will actually be meaning that you have excessively misbehaved to the extent that if the head has had you and me the executor. So I issued out another copy of a third chapter that we're supposed to look at by the end of this term. And I am working on the assumption that everybody has at least moved a step. Are we together? Now let us look at sinking and floating. Yes. Yeah. About Hooke's law? Yes. About Hooke's law, the calculative examples, I did not explain what and where exactly. Joan is always putting us on check. Now, calculative examples of Hooke's law are particularly partitioned into two parts. One is if any force is applied onto a material that is elastic. Are we together? And then it extends. Maybe let me give an example. From Hooke's law, how does the law state mathematically? Patience, come out. Come out. I will slap you. Come out. Come and sit here. Tracy, do the same. Come with your bag. Come with your books. Tracy, do you know English? I've said do the same. And Christine. I am struggling to again make people understand you are smiling at the friend. I will slap you people. Sit here. Where Christine, go and sit there. Sit. Hey, I will slap you. Say sit. Now let me again see you teething. How does the law state mathematically? Not K. F equals K, KE, where F is the applied force. K is the constant of proportionality, and then E is the extension. So originally, it is F directly proportional to E. So when you remove the sign of proportionality, that is when you bring in a constant of proportionality, which we say that K is called, it is a constant of elasticity. So in the calculative examples, number one, we can be given either the force, you can have the force, and the extension, and your task is to find K. Did we look at that? Did we look at that? Where you have either F or E, find K. Or you can have K and E, you find F. Or you can have F and K, you find what? You find E. You can have F and K, where you're supposed to find E. Did we look at that? John. Then you can have F and E and you're supposed to find K. Right? Then you can have K and E and you're supposed to find what? F. So now, John is asking for a case where you have F1, F2, E1, E2, and you're supposed to find K. Isn't it? Or you have F1, F2, E1, and you're supposed to find E what? E2. I remember talking about a point where you can have the same elastic material, right? You can have the same what? Elastic material. And you apply a force, F1. Let us assume this is a spring, and you apply a force F1 on a spring whose constant is what? Is K. You apply a force F1. This spring, it gives you an extension E1. Are we together? You can have a spring whose constant is K, and you apply a force F1, then it extends E1, right? Then you apply the same spring. You give the same what? Spring, and give it a force F2, right? This spring is going to give an extension what? An extension what? But the constant is not going to do what? To change. Are we together? So if you have such a scenario, or if you have such a case, Hooke's law is going to be F equals Ke, right? The law does not change. What are going to change are the subscripts. That for case 1, you apply the force F1, are we together? And it gave you an extension E1, right? Are we together? So when you make K the subject of the formula, what do you get? If you make K the subject of the formula, what do you get? Divide both sides by E1. You'll have K as F1 over E1. Maybe I can call that equation 1, which I get the expression of K from case 1. Applying the same spiral spring. Now, if I proceed to F2, a case 2, if I proceed to a case 2, again, Hooke's law is going to do what? To apply. So we shall have F equals Ke. But what force is this? F2. And it produced an extension what? E2. If I make K the subject of the formula, what do I get? If I divide both sides by E2, I'll have K equals F2 over E2. Joan, didn't I talk about this honestly? Sure. Joan is insisting. Class, did I talk about this? And we said that if this spring has a constant K, and the same spring has a constant K, Joan, really, didn't we say that we are going to express this K as the same as this K? This K is the same as this. And we say that K is going to be F1 over E1, all right? The same K equals to what? Equals to F2 over, and I again asked, what if I apply the force F3 and it gives an extension E3? What do we get? What happens here? It becomes F3 over, Joan, didn't I talk about this? Then we said, what if again we apply a force F4, but on the same spring? If we apply a force F4 and it produces an extension E4, what are we going to get? F4 over, Joan, didn't I teach this? Huh? Joan, tell the class, didn't I talk about this? Yes, Mr.
You come and grab you. You're competing in the school. Friday is not study, Thursday is not study. You can't keep like that. Don't back in the camera, boy.
And these are the people who even displace my camera. You people, you are late. The dogs doesn't know you. So, John, honestly, I remember I taught this. Maybe one thing I did not do is we did not go through the examples. Yes, Juana Daniel. Good morning. Thank you. So let us try the two examples. Can we listen? Let us try the two examples for Joan to get satisfied that at least we have done it. Okay? Let us try to go through the examples. Example 1. No, let Joan only read. Read again for us to understand the analysis. A coiled spring is stretched by, right? Which means we have, can you look here? Which means we have the extension E1, right? What is E1? 0.05. E1 is 0.05 what? Meters. The weight that acted on the spring to extend by this was F1, or you can call it W1. F1 is 5 newtons. Go on. I am interested in the word the same spring. If it is not the same spring, K's are not going to be the same. Yes, sir. Jambo, sir.
Nyoka online yako
Wakagala. Ate katika rekodi.
Mu channel che
YouTube channel.
Emamanya che
Tebandike Israel. Yes, sir. Butu Serex.
May come here with harmonize. But you are behind. By requesting that master, you our doors, to the teacher, that we shall never repeat again coming.
So we are not delayed.
This one has.
Mom, okay, take your birthday.
What I've requested.
Okay,
I said,
sir.
let me request my master. If he allows you to. On their behalf.
Okay, sir, it's okay. Let us enter. Yes, ndugu Muhindo, habari ya asubuhi. Okay, settle very fast. I've said I am interested in the word the same spring. It can only be the same spring, then you consider the fact that it has the same what? The same constant K. Are we together? If it is not the same spring, don't dare make the assumption that the constant is the same. The same. Continue, John. Now, weight is force F2, right? So F2, you are being asked that which one. So you don't know it, right? And then extension E2 is 0.03 meters. Now let us apply the fact that the same spring but different forces acted on it and it produced different extensions, right? So you can decide to first find the constant K. Are we together? You can decide to first find the constant what? K, saying that from Hooke's law, from Hooke's what? F equals KE. Are we together? So F1 will equal to K E what? E1. F1 is, what is F1? 5 equals K, do we know it? Times E1. What is E1? 0.05. Now from here, the remaining work is mathematics. To only get K, what do? We divide both sides by 0.05. And then we cancel that one which has the same numerator and denominator. So we remain with K equals 5 divided by 0.05. Pardon? 100. And the unit of K is Newton per meter. But nobody asked for a K. Are we together? Nobody asked for a K. So we are looking for F2 of the same spring. Are we together? So we shall have F again from Hooke's law. Again from what? Hooke's law. Again from Hooke's law. F equals K what? KE. Are we together? But this case we are using F what? F2 and E what? E2. So what is F2? We don't know it. K is 100 times E2. 0.0. So our F2 is going to be 3 newtons. Are we together? That is approach 1. Approach 2 is coming here. Approach 2 is coming here and extract out an equation that has F1, F2, E1, and E what? E2, which is this one here. Are you seeing it? Are you seeing it? So we shall have F1 over E1 equals F2 over E2. So alternatively, we shall have from F1 over E1 equals F2 over E2. Alternatively, from F1 over E1, which is the definition of a K, the constant. So from F1 over E1 equaling F2 over E2, if we had another force F3, still we can find it from the same expression. Are we together? So do we know F1? What is it? 5. E1, 0.0 equals F2. We don't know. Over E2, 0.03. Now from here, the remaining work is algebraic gymnastics. So we shall cross. Now it depends on how good mathematically you are. It depends on how good mathematically you are. Somebody can decide to squeeze this first. When you squeeze this, a colleague told us that you get 100. Isn't it? So we shall have 100 equals F2 over 0.03. Now this is 100 over 1, I think. So what do we do here? Cross multiply. And you have your F2. Any number times 1 is 1. Is that number? I'm sorry. So we shall have F2 equals 100 times 0.0, and we get 3 newtons. So basically those are the dynamics to do with loads being put on the same spring, and the spring gives you different extensions. You can find any of the unknown applying the equation. Joan, are we together? We try out example 2. Because for example 2, now, example 2, we are provided with the force that was applied onto the spring, isn't it? We have the force that was applied on the spring, and it produced an extension, right? But now the question is asking for the mass, isn't it? That can be loaded on the same spring and it gives a particular extension. You, my daughter, you've come in late, come and rub off. But don't rub the margins. Joanne can read the problem. Don't rub the margins, right? Read the problem.
When the force of 12 Newton is applied on the spring, it produces an
Where you're not.
extension of 0.08 meters. What mass of an object when hung on the same spring
You might look for the book.
produces an extension of 0.08.
Now, a particular force of 12 newtons was applied onto a spring, and the spring stretched, produced an extension. Remove it. When it produced an extension, what is now the other mass that is supposed to be loaded, right, onto the same spring? This is what happened. Solution. A spring is this one here. When they apply the force of what? 12 newtons, it produced an extension of 0.08 meters. This is the spring, case 1. Are we together, ladies and gentlemen? Now, case 2 is what mass are we supposed to load here? What mass are we supposed to load here? Such that this mass makes the spring to stretch to how many meters? 0.06. To 0.06 meters. Ideally, the diagram I have is not realistic, but I think you can understand. Because if this force produces an extension of 0.08, it means 0.06 must be less. Okay? Are we together? So the diagram I have is not realistic, but for purposes of demonstrations, you can understand, right? Ideally, this must be smaller than that. So this must be like this. The mass M2, and then the extension is 0.06 meters. Are we together? Now, in this case, we are still going to follow the same steps, right? But somewhere we shall move an extra mile of finding the mass from the definition of a force. So at the beginning, we shall find a force F2. Are we together? From the first principles, we shall find the force F what? F2. But in our senior one, we studied that how do we get the weight or the force of a body that is suspended and is swinging freely? How do we get the force of a body that is swinging or suspended and it is freely swinging? Force equals mg. So which means that F2 will also be m2, but g cannot be g1 or g2 because g is the same. Now let us begin from which option can we use? Can we take the option of going through each, or we can quote the law that F1 over E1 equals F2 over E2? I think this is a shortcut. So F1 we know, E1 we know, F2 we don't know, E2 we know, but nobody asked for F2. We shall be getting M what? M2. So if I substitute, F1 is 12 out of E1 is 0.08 equals F2 we do not know over E2 0.06. Now a good mathematician can squeeze this. What do you get? 12 divided 0.08. Yeah. 150 equals F2 over 0.0. Balance here and cross multi. So you'll have F2 as 150 times 0.06. Joan, again today you've not come with a calculator. You get? So F2 is 9 what? Is now we're supposed to find M2 from F equals to what? To mg. So from F equals mg, F is 9 equals m that we are looking for times g is 10. So to get m, we divide both sides by and have m equaling to 0.9 what? 9 kilograms. Joan, are we together? Sinking and floating as a new chapter. Sinking and floating. Sinking and what? And floating. Or floating and sinking. Somebody is quoting exactly what they have. Floating and what? Floating and sinking. Now, I don't want to go, a little joking, but this word it exists in English. But the problem, floating and sinking. Well, what do people understand by the two? In senior one, you studied about density. And you said that density is, how did we define density in senior one? Can we come back to class? How did we define density in our S1? Yes? Density was defined as the mass per unit what? Volume of any substance. Density was defined as the mass per unit volume of a substance. And we said that density or sinking and floating of substances is also related to density, right? What did we say about sinking objects versus floating objects? Label. What did we say about sinking objects and then floating objects with respect to density? Well, we say, I can hear people are vibrating behind them. If I have not given you a chance to talk, can you please keep quiet? We said that if you have a liquid X, if you have a liquid what? X with the density rho X. With the density what? Rho X. Then you have any other a substance Y, right? With density rho Y. If you have a substance, if you have a liquid X, whose density is rho X, and then you have an object, let us, think it is a solid, but also liquids can either float or do what? Or sink. But let us begin with a substance that is a solid in nature, whose density is rho Y. If the density of a substance, rho Y, is less than the density of a liquid, rho X, what happens? If the density of a substance rho x, rho y, is less than the density of the liquid, rho x, what will happen to the substance? The substance is going to float. All right? What if the density rho y is greater than the density rho x? What will happen to the substance? The substance is going to sink. Now, there are a number of observations that we need to make first before we get into the density details. But first and foremost, the competence or the general objective of, or as to why we are looking at this thing is, did you take note? The competence is, Dorothy, read for us the competence. Generally, why are we looking at sinking and floating of objects? You see, Nakavito is telling me, you know, me, I'm this. That word is sinking, not thinking. Actually, it's only the Wanyankole who can read thinking as sinking, and then sinking as thinking. So, Dorothy has told us that, ladies and gentlemen, by the end of this chapter, we should be in position. Where is my daughter, Evers? By the end of this chapter, Evers, even though you porously entered, you should be in position to explain. I told you the other time when the deputy academics was in here that the issue of explaining is a big business. To explain, it goes beyond defining. If they tell you to define the physics teacher, you can define me in just one line of the book. This is a man who ABCDXYZ. Just show a definition is a brief description. But now if they tell you to explain, maybe you want to meet a group of people and you want to explain to them who a physics teacher is. My friend, you must come up with such a handout, explaining, such that if somebody meets me even during night, that person can tell, according to the explanation they gave us, this is the man. So by the end of the chapter, sinking and floating, all of you, if not the majority, you must be in position to explain sinking and floating, and go ahead, show the real life applications or where sinking and floating is applied in everyday life. You know, I usually inform you people that we don't teach you only to pass exams, but also to fit in society. We are going to see the observations here that are brought about by that apparent loss of weight of the objects that people do not look at and consider, or they do not take serious. Are we together? So you must be in position to, when you go back, explain to the siblings what sinking is at length and what floating is at length. Then give them real life examples. But how are we going to do that? Outcomes. Dorothy. Outcomes, they are basically two. Okay? Read one by one. Good. Now, everybody must have read through at least, because, like, coincidentally, I can appoint you to also read for the class. So as somebody is reading through, everybody, by the time you are trying to take the notes, you are reading through. So don't come across a word and begin to add 2 words by 2 words. So outcome 1 is we must be in position to understand the concept of sinking and floating, in terms of forces, in this case, we are not going to understand it in terms of densities. Are we together? I started by reminding you that it exists in terms of densities. But now here, we are going to look at it in terms of now the forces acting on a body. Which body is submerged? You know, to submerge? To immerse, to put something into a liquid or a fluid. You know, in church, especially the Pentecostal church, they have baptism, where they get an individual like this, they close the nose and submerge into the water, then they bring you out. For them, they say that that is when you have died and resurrected. I have nothing much to say about that, but what you should know is submerging is to deepen something into a fluid. Learning outcome 2, Dorothy. Learning outcome 2. I'll repeat. Can we listen? The what? Archimedes or Archimedes principle. Now you see, can we listen? By the end of the chapter, sinking and the floating, we must be in position to understand first and foremost. Then apply a certain principle called Archimedes. Archimedes is an individual, a scientist, who studied this experiment and then proved that it is 100% true. So we have two major outcomes. One, to understand the concept of sinking and floating, basing or in terms of the forces acting on the what? On the body. Which body has been submerged into a fluid in which it is either sinking or on which it floats. Then two, there is a principle that actually it governs all whatever we are going to look at. So let's look at the observations. Let's look at the observations here. Let's look at the observations. My daughter here, read us observation 1. If you lift a bucket, she does not have the work. Observation 1. How many of you have ever tried this? When water is, let us say, in a tank, and you want to scoop off a small bucket or a basin, when you are picking it from inside the tank, is the bucket heavy? Is it heavy? When you are lifting it from inside water of the tank, that bucket seems to be a little lighter. But when you pull it completely out from the tank, what happens to the bucket? Now it becomes heavy. That is observation 1. We are going to explain that using sinking and the floating. Observation 2. When you go swimming, I don't want to say if anyone, because I'm sure if not all of you, the majority of you have never gone for swimming. And then the other best example that I would use, can we listen? Hey, the other best example that I would use, again, I'm sure none of you has ever been on a lift. Yes. Now, listen. Well, can you listen to me first? None of you has ever been on a lift First listen. Can you listen? I am saying none of you has ever been on a lift and the lift is accelerating downwards with an acceleration A equals to G. I repeat, none of you has ever been on a lift and the lift is accelerating at an acceleration equaling to G. However, whoever has, I will beat the group here. Whoever has ever been on a lift, this is what it happens. When you are on a lift and it is descending, to descend is to move downwards. When you are on a lift and the lift is moving downwards, it means that when you stand on a lift, if Prosi stands on a lift, Prosi is going to exert, can we listen please? I will cancel this. When you stand on a lift, you exert your weight on a lift as W. Then the lift gives you an equal but opposite what? Reaction, R. All right? Now, a person who is standing on a lift and the lift is not moving, that person, his or her weight is what we actually call the actual weight, as we are going to see even here in the fluids. When you stand on a lift, let us assume this is a lift, and the lift is not moving upwards or downwards, the weight you get when you put a weighing scale on the lift, what it reads is your actual weight. Are we together? But when you stand on a lift and the lift moves downwards with an acceleration A, I don't want to hear anybody vibrating. I'm going to begin chasing you out now. When you stand on the lift and the lift is moving downwards, it means that your weight is greater than the opposition force due to the lift. So you will have your weight minus, do you remember how we got the resultant force? Do you remember how we got the resultant force? Yes. If two forces act on the particle but in opposite directions, the resultant force is the difference. So you will have the weight minus the reaction equals the resultant MA. This means that, this implies that your weight is going to be the reaction. If I take this on the other side, if I take this on the other side, I'll have the reaction plus MA. So when you stand on a lift and the lift is moving downwards, ladies and gentlemen, if you put a weighing scale and you stand on that weighing scale, it will show you that your weight is greater. That weight you will be having when the lift is moving downwards, that weight is going to be greater than your actual what? Your actual weight. Are we together? Are we together? Wake up that girl there. Are we together? When the lift is moving downwards, you feel more heavier. You feel it. Now, when do you feel lighter on a lift? When the lift is moving up, when the lift is moving upwards, you feel like you are lighter. And when you put a weighing scale on that lift, you realize that the weight you will have is going to be less than, when the weight is moving upwards, your weight is going to be less than the actual weight. Now, those forces that make you feel lighter when a lift is moving upwards are the same forces that make you feel lighter when you are in a swimming pool. In a swimming pool. That's why we are trying to make an observation here, that when we go swimming, we feel lighter or we feel a little weightless in water than our actual weight. Observation 3. A large ship not endiga or entama. I think in Runyankole you call it entama. I mean a ship, one of the means of, water transport. A large ship, those of us who have got an opportunity to travel by water transport, you realize that a ship is as big as, actually, I can't compare it with any structure here. But for it, it floats on water. And you get a small needle. A small what? Needle or a pin sinking. All those observations are going to be explained by those forces that act onto a body when it is either submerged or placed on top of water. All right, continue. Therefore, an object, ladies and gentlemen, it weighs less when in water, or we are being particular, in the liquids, but an object cannot only be placed in water. There is a historian, those of you who will do history at HSC, there is a man called, is it Napoleon Bonaparte, something, who dumped himself into a jar or a tank of acid after fighting a certain war. I don't remember, was it World War II? I will inquire from the historians. So you can also be placed in another liquid which is not what? Water. So you can either be put in acid. Yes. You can be put in porridge. You can be put in milk. You can be fried in cooking oil. Why can't you? We get cases here when somebody comes to school with a very big wound and you ask him, what happened? Somebody tells you, I was cooking. Then you ask, were you cooking food or cooking yourself? So meaning that you have chances of being submerged in cooking oil. So we are saying that anything placed in, let us make it a general thing, anything placed in any fluid, it has chances either to float or to do what? Or to sink, like the diagram we have there. That if you have a ball, it can either float, all right? It can either float or, but depending on the forces and the conditions available. Continue. Who are those ones? Where is the professor? Read the conclusion. Start from therefore. Stop there. Therefore, an object weighs less in water, which means that if we take the weight of Joan in air, how weight is going to be, let us assume the weight of Joan. If you sit close to a neighbor who is dozing, please wake them up. I'm saying if you take the weight of Joan in air, let us assume it is 50 newtons. Are we together? When you take the weight of the same person in water, the weight of Joan is not going to be 50. It is going to reduce. So it can be 22 newtons. Meaning that if you dip Joan in water, you can carry her with one hand. Even the procy. When you put procy in water, it becomes a piece of cake to pick her from water. But I want to assure you that you cannot carry her on air or in air. You actually need a car carrier. You know, a car carrier. All right, continue, Professor. Have you seen the origin of the name of the principle? Have you seen the origin of the name of the principle? So all those observations that I have made, one, an individual weighs less in water. Two, it is easier to carry a bucket of water while in water than when it is out of the water. Three, you feel lighter when you are in water than when you are outside of the water. All those observations, young guy, all those observations can only be explained by a principle called what? Called Archimedes. Called Archimedes principle. And we are saying that the principle was studied. The principle was formulated. The principle was given birth to by a Greek mathematician called Archimedes. The next time we meet, we shall start from Archimedes' I beg to stop there.